Assalamu alaikum. Welcome to the third lecture. We'll speak about sieve analysis, right? Sieve analysis, طريقة التنخيل, sieve analysis. We said that to classify soils to gravel, sand, silt, and clay, right? Soil may be gravel, sand, silt, and clay. Okay? We have to use sieve analysis. Sieve analysis. Sieve analysis, it's a collection of sieves with different openings, okay? And at the end we have pan. You did this test when you get material engineering, right? So we have collection of sieves with pan at the end and a cover, okay? Now sieves may be 100, maybe more than that, maybe less than that. We have different ways to consider sieves, but let us study or have US standard sieves, okay? US standard sieves. We have several standard sieves, but we will use US standard sieves. This table exists in your textbook, okay? Which is the international edition, okay? Because you could not find 5th edition, so you can buy international edition. Okay, now we have different sieves with different openings. We use openings, okay, but nobody will remember after all that this one is 9.51 millimeters, but that one is 1.18 millimeters. Nobody will remember this. Nobody will memorize all these, okay? We prefer to use easier way. We give them numbers. We say sieve number 4, sieve number 16, sieve number 20, sieve number, etc. Okay? So, for example, sieve number 4, it has an opening of 4.75 millimeters. Okay? This is an important sieve. We will say why later. Okay? We have different sieves, 5, 6, 7, 8. These are not all the sieves. Okay? I just chose some of them. Okay? Sieve number 4, 8, 10, 16, 30, etc., 40, 50, 60, 80, 100, 120, 170. I said that there are many other sieves, okay? But these are some of them with their openings. What is important for us? Sieve number 4 is important. Why? Why? Okay.
It's separate coarse and fine.
Not coarse and fines. Okay? Let us remember. Let us go back to this. Remember. We have soil is either coarse, right, or fines, right? Coarse or fines. Now, what is the borderline between coarse and fines? By the way, coarse means gravel and sand, right? These are coarse, gravel and sand. While fines, it's silt and clay, right? So we have coarse, fines. Coarse consists of gravel and sand. Fines consist of silt and clay. Okay? Now, the borderline between them, between coarse and fines, is a number. I'll tell you later. The borderline between sand and gravel is 4.75 millimeters. Okay? As you remember, we studied this previous lecture. We said that we will use between gravel is more than 4.75. Remember? Gravel is more than 4.75. So, gravel is the borderline between 4.75 is the borderline between gravel and sand. This is number 4. This is number 4. So when we come back to where we were, okay, number 4, 4.75. This is important. Why it is important? Because it's the borderline between gravel and sand. Okay? This is important. So we should have it. We should have it in our sieve analysis test. We can ignore sieves above it. We can ignore number 8, 10, 16, whatever. But we cannot ignore 4. Why? Because it's a borderline. Okay? It's a sieve with a borderline between gravel and sand, whatever. Okay? Sand, silt, and clay. Any particle doesn't go through number 4, so it is gravel. Doesn't go through, so it is gravel because it's greater, it's bigger than 4.75. Any particle goes through number 4, 4.75, so it is sand, and maybe silt, and maybe clay. Okay, because it's smaller. It's smaller. Get it? It's smaller. Okay. Now, another sieve that we should have also, it should be there, is number 200. Number 200. Why? Because its opening is 0.075. We have number 200, 0.075 millimeters. This is the border between coarse and fine. So it is important because any particle goes through number 200, it's fines. Okay? It is fines. It is silt or clay. Please take care of your mobiles. Okay? Any particle that goes through number 200, which is 0.075 millimeters, it's considered fines, which may be silt, may be clay. Okay? Any particle doesn't go through number 200, it's greater, so it is sand or gravel. Okay? Any particle goes through number 4 but doesn't go through number 200, so it is purely sand. It's sand. Okay? So that's why we should have always sieve number 4 because it's a borderline, sieve number 200 because it's a borderline. Okay? And of course we should have a pan. Okay? Because anything goes through number 200 and collected in the pan, it is fines. How we can know how much fines we have? Just by collecting them in a pan. Right? We cannot put the last sieve to be number 200, then whatever passes, it goes to the ground. Okay? We should collect them, right? We collect them in the pan. So, we go back. Okay. Okay. We were here. No, this is the example. Okay, we go back. So, that's why, you see, by the way, you don't have to memorize all of these numbers and openings, okay? But you have to memorize 2 of them at least. You have to memorize that number 4 is 4.75, number 200 is 0.075. You should memorize this, okay? I don't have to tell you, for example, in an exam that sieve number 4 is 4.75. Or if I told you, okay, a sieve which has an opening 4.75, you should not ask me whether it is it number 4 or what number. I will not tell you, okay? So you should memorize just these 2, because these are the border sieves, okay? Number 4, 4.75, number 200, 0.075. You should memorize these, okay? That's why when we do sieve analysis test, okay, we should have number 4, number 200, and a pan. They should be there, 3. So already we have 3 sieves. How many sieves we should use? How many? Okay. To draw a straight line, we have to have a minimum of how many points? 2 points, right? To draw a straight line, we should have a minimum of 2 points. But to draw a curve, maybe 3 good, but maybe not good. Like, for example, these are 3 points. Okay? Do they explain the behavior of this curve? It may be like this. You see? So 3, good, but 4 is better. 5 is better. 100,076,000, etc. It's good. You see how much are these points? How good is the curve? Or more obvious, more clear, right? But of course we will not draw millions of points to draw a curve, maybe 5, 6, 7 points are enough. So my advice for you is to have at least 5 sieves, around 5 sieves including the pan. Okay? If we get out of them 4, 200 and the pan, these are 3. So let us have another 3, another 4. Between 5 and 7 all together, sieves including the pan, they are enough. Okay? 5 to 7, they are enough to draw a curve. 5 to 7. 5 to 7, okay, let us say 7. 7. We take from them 4, 200 pan. So we need another 4, right? But we have to distribute them in a good way. Like, for example, if we go back to the where we were. Okay. Now, if we go to number 4, for example, if we have sieves and then we distribute it like them, number 4, number 10, number 16, number 30, number 200. Is it good? I have to have sieves between number 4 and number 200. So let us distribute them equally, right? For example, number 4, number 40, number 80, number 120, 160, 200. Good intervals, right? I cannot just put all together. I cannot draw a line by having 1 point, 2 point, 3 point, okay, and last point. Especially if it is a curve, right? So it's better to have good intervals. Okay? So we have to use number 4, number 200 a pan, and another 3 or 4 sieves distributed equally. Okay? This brings us to the should be distributed fairly. Okay? So when we have to draw a sieve analysis, when we have to draw what we call it particle size distribution curve, we should have 4, 200 and pan. These are needed. Okay? They should be. Okay? We have to have 3 to 5 additional sieves to have a total of between 5 and 7. Okay? And the other sieves between 4 and 200, they should be distributed fairly. Okay? Good. Now we did how we do the test. You know that we bring a sample, weighing the sample, right? For example, the sample is 500 grams. Okay? Then we did the test. Of course, then we will distribute. The first sieve will have that amount, right? Second, third, etc. Then we collected all the weights. Okay? We found, after collecting all the weights, that the total weight it was 500. Now the total weight is 502, 501, 502.5 grams. I mean, any number above 500. Is it acceptable? No. Why? Errors may happen. Errors may happen, you know. We are human. So, is it acceptable? Say it loudly. Yes. Say it loudly.
Yes.
Yes. Yes. Okay, then you are wrong. I'm waiting for somebody to say yes, to say no, it's not acceptable. Weight, not acceptable. Above the total weight. More than the weight given, it's not acceptable. Okay? I put 500 grams, they should not be 500.0000001. Because there must be a mistake. What should we do? What should we do? Repeat the test. Okay? It is not allowed to exceed the total weight of the sample that was from the beginning put in the test. Okay? I put 500 grams. I should not exceed 500 grams. I put 400 grams. I should not exceed 400 grams. Acceptable? Okay. Now, I put 500 grams, but after collecting all the weights in all the sieves, I found that it is 497 grams. Why? Okay. Now, there is a human error. There are always human errors. There are always mistakes. There are always something happens, especially when we are dealing with, when we deal with souls in number 200 or passing number 200, as if we are dealing with dust, dust. So it may leak here or there. It may be lost here and there. So there may be some losses, but they should not exceed 3%. In some cases, in some standards, they consider 5% acceptable. Okay? For us, 3% is enough. Okay? So, we will not accept anything above, anything greater, anything higher than the weight, the beginning weight. Right? We can accept a 3% error. If you found in some books and some references 5% errors, okay, no problem. But here we will accept 3% error. Okay? Let us have an example. Perform sieve analysis for a soil sample weight 450 grams. Okay? I brought a sample, soil sample, 450 grams. Okay? I put them in the sieves. Number 4, 10, 16, 30, 40, 60, 100, 200, and the pan. Okay? I don't believe that this is a good distribution. But okay, this is what we have. I put the 450 gram on the sieves. Of course, I should cover them tightly. Okay? I should cover them tightly. Then we will put them in the shaker, right? Remember that shaker, which is always not working? Okay? Is it working nowadays? Okay, the guys can help. Okay? Then we will shake the sample. For how long? 15 what? Centuries?
Minutes.
Years?
15
15 minutes, okay. 15 minutes. For how long we should shake the sample? 15 minutes? You did like this 10 minutes? Okay. Here we go back to engineering sense. Remember? Big plus engineering sense. If I am dealing with sand or gravel, I see that the sample is sand and gravel. Maybe 2 minutes are enough. Okay? But if I'm dealing with, seems to be clay, you see, clay, so maybe I need half an hour. Okay? The objective is to get the result of shaking. It's not to be limited to a time. It's not just, okay, 10 minutes, 10 minutes, enough. No. It's that, did we reach the objective? The objective is to separate particles from each other. That's why we shake them, right? So, 10 minutes may be good. Sometimes half an hour may be needed. Sometimes maybe an hour needed. We need to shake the sample well in order to get all particles away from each other and let every particle go. Every particle goes through the opening. Okay? So this is the time of shaking. After that, we will collect the weight, the soil from every sieve, right? And record it. For example, sieve number 4, nothing, with opening 425. This is an opening one. We found that there is no soil on it. I mean, all the sample went through the opening. Okay, no grams, 0 grams. Sieve number 10, with opening 2 millimeters, 0. Okay, all particles went through the opening. Sieve number 16, I found 9.9 grams. By the way, we have sensitive balance. You see, we have sensitive balance there. I think it reached 1.01 gram, right? 0.01 gram. So that's, don't say, okay, 9.9, let it be 10. No. You should be precise. Okay, you should be precise. 9.9, then 24.66, then 17.60, then etc. And then in the pan we had 278.99. By the way, I collected these numbers. They were 450. Is it okay? Is it okay? Of course it's okay, because 450, it was 450. Now, this mass retained in gram, can I make it in percentage? What percentage? Okay. Now, here, 0%, 0%, 9.90 over 450 by 100%, it is 2.2%. The other one is 5. Now, he used here a way that I may use a different way. Remember, here we have a mistake that usually students make. Remember, because here he put 9.9 over 450, 2.2, 24, etc. It's like this, okay? He had percentages, right? When he moved to calculate the passing, look what he did. 0, then 100%, right? 0, then 100%. 2.2 out of 100%, it's 97.80%, right? Then if we took 5.48 from the 97.80, remember, it's cumulative. Remember this. You may do some mistakes here. It's cumulative. Otherwise, this will be zigzag. That's why it's, you see, 100 and goes down to 0. It's cumulative. You may do it here in this step. Some do it in this step. Okay? Some do it like this. Mass retained, then mass passing, then percent passing. Okay? It's up to you. Use whatever you like, but at the end we will have percent passing versus opening, which is diameter, right? Which is diameter. Particle size, we mean particle diameter, right? We said previous lecture. Particle size, we mean diameter. Okay? Then we will have a relation between particles diameter and percent passing. And it has always to begin from 100 and end with 0. Okay? So it's cumulative. You see, look. 62 plus 1330 is 7530, right? Plus 780 is 38, you see? Plus 5 is, you see? Because it's cumulative. Okay? Otherwise, you will have a problem. It will be a zigzag, not a curve. Get it? Because, guys, 9.9 retained in number 16. In number 30, I found 24.66, but also this number retained, right? But I already wrote this number, right? Okay. Now, after that, we go to put this in a particle size distribution curve. This is typical particle size distribution curve. We will have here diameter, grain size. You see, it's in log scale. So this is, we call it semi-log curve. Semi-log. Why semi-log? Because this is logarithmic, while this is normal. You see, 0, 10, 20, 30, 40, etc., 100. You see, it's similar intervals, right? So this is normal, but this is not. You see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, it's getting smaller, right? Because this is logarithmic. So because it's logarithmic and normal, it's semi-log. Okay? If it was logarithmic and logarithmic, so then it is log. If it is normal and normal, then it is normal, right? Here, okay. So here we will have semi-log scale. Okay? What do we have in this semi-log scale? We have 1, 2, 3, 4, 5, 10. Okay? 0.1, 0.01. You see? Now, what we have to do is to plot the numbers that we got here. Let us remember. I'll go back. Oh, the same page, right? But we have to go above. Remember, somebody write in your papers. Number 4, we had 100%, right? Remember this, write it, because I will not go up and down all the time. Okay, number 4, which is 425, it has 100%, right? Number 10, which has 2 millimeters, it's 100% also. Number 16, which is 118, it has 97.80. Let me go immediately, and I'll continue later. Okay, so it's first one is number 4, right? Which is 4.27, 425, 475, 475. Look, 1, 2, 3, 4. This is 5. So 4.75 somewhere here. This is 4.75. How much we have percentage? 100. Okay, so this is the point. 100. Okay. The next one is number 10, which has 2 millimeters, right? 2 millimeters. This is 1. This is 2. 100 also. I don't have to draw between 100 and 100. Okay. We will begin from where we go down. The next one is number 16, right? What is the opening of number 16? 1.18. 1.18. This is 2. Okay? So it's almost 120, right? So it's somewhere here. Somewhere here. How much? How much? 97. So somewhere here. Okay? Somewhere here. Now, you see? The next one is number 30, right? 0.6. 0.6. How much? 20. How much percentage? Here. It's 92.32, right? What was the opening? 0.06? 0.6, right? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. This line. How much? 93? 92. This is 92. So it's here. Okay, we continue. You see? Then the next one. How much? Number 40. 0.425. By the way, this is important. Number 40, important. But later on. It has 88.1. Then number 60 with the opening, etc. Then last one, number 200. How much? 62%. Number 200, which is 0.075, 0.01, 0.2, 0.3, 0.2, 0.03, 0.4, 0.5, 0.6, 0.75. This is the one. How much? 62. 62 here. So I already make particle size distribution curve. You see? Easy. It is easy. We draw the particle size distribution curve. Anybody has a question? Do you have a question? Okay. You may not like this curve because it's not complete. Why? You see, 62% of the sample we did not classify. It's just we say that we have 62% of the sample finds, right? But what after? We don't know because we did not reach 0.001. You see? Okay, I'll explain this later. But let us have this. Okay, this is a particle size distribution curve. Before I go to this, let me go another page. Advantages of using sieve analysis. Why we have to use sieve analysis? Why we do it? Okay. Now, first of all, by just a glimpse of look, okay, we know percentage of gravel, sand, silt, and clay immediately from the. We go back here. Look, I will use the green line. Okay. Now, 4.75. Here is 0.475. Okay, I can draw this line. 0.075. Here is 0.075. Now, what does it mean? Look, here, this is gravel, right? Here, this is sand, right? Here, fines, which is silt. Maybe after that I can say clay. You see? Now, when I look to a curve like this, immediately I say I have sand, right? Immediately I say I have sand, right? Now, if I have a curve like this, no, I don't want to use this one. Let me use this one. What does it mean? I have this % of gravel, and I have sand, and I have... Now, if I have a curve like this, I don't have gravel, I don't have sand, you see? So just by a look, I can immediately know that I have this much gravel, this much sand, this much silt, this much clay, right? So that's why we have sieve analysis, and that's why we draw this particle size distribution curve. Because from just one look, I will know that I have how much, like for example, if we have this, it's just sand. If we have this, I have half sand and half silt. You see? So that just by looking at this, we can okay? So this is the first thing. Second thing, knowing type of curve. Knowing type of curve. Let us go back. Now, this is sand, right? This curve says that we have a sandy sample, right? No gravel, no fines, right? Okay, what about this curve? It's also sand. But is there any difference between this curve and that curve? Of course there is a difference. So it's not just it gives me how much sand, how much gravel, how much silt, how much clay only. It also describes what kind the distribution, the real distribution. So we know that, for example, this one we call it well distributed. Why it is well distributed? Because I have different sizes of particles. I have big, small, medium. So it is well distributed. While this one, it's poorly distributed, or maybe uniformly distributed, because all particles are of the same size almost. You see? So from even a look, I can say, this is well graded, this is poorly graded. You see? What about this one? Poorly graded, right? What about this one? Well graded. You see? So just by a look, I can know that I have poorly graded or well graded. Wait a minute. Now sometimes I will have this type of curve. It was going smooth, uniformly, then as if there was a gap. You know what gap? Okay? Then return to a smooth curve. Okay? This we call it gap graded. So, this is another advantage. The first advantage, by a look, I know how much gravel, how much sand, how much silt, how much clay, right? This is one. Second thing, I will describe this soil. This is well graded, this is poorly graded, this is gap graded. Okay? Now a question. Do you prefer to deal with uniformly graded or poorly graded or maybe gap graded? Uniformly graded. You like to deal with uniform. Who's with? Who's against? And the majority is not with, not against. You are real Arabs. Okay? ميم عين عين. شايف؟ معهم عليهم. You should have your own decision, your own right, your own idea. Okay, he says uniformly graded. I say poor graded. Okay, that's good. That's good. Guys, it is up to the work I will do. In some areas, I need poorly graded. It is good to have poorly graded in some areas. In some areas, I need to have well graded. So it's not that this one is good, that one is bad. But this one is good for this job. This one is bad for the same job. This one is good for the other job. And that's bad for that job. You see? Like, for example, if we have a retaining wall, retaining wall. Here we have highway, street, okay? And this is soil here. We will have a problem, like we have it in several places in our country, that during rain, water will come here, and then it will pressure the retaining wall, then there is a collapse, right? So usually what we will put here behind the retaining wall, we have to put some type of soil in which we allow water to go through and to be collected here in somewhere and then to divert it away. You see? Now, is it better to use poorly graded or well graded? Poorly graded is better, you see? So, then it is related to the type of job that we are doing. In some cases, poorly graded is good. In some cases, well graded is good. Okay? Now, we go back to the same page. What else we can get from the sieve analysis, from particle size distribution curve? First, we will know gravel, sand, silt, and clay, right? Second, we will know that poorly gap graded by just a look. Okay. Third thing, we will know CU and CZ. These are two parameters. What are they? CU is called uniformity coefficient. Uniformity coefficient. It is D60 over D10. D60 over D10. What is D60 and what is D10? The diameter at which 60% of the sample passes through. Okay? So I'll get this number. How much? 1.1, 0.2, 0.3, 0.4, 0.46, for example. Okay? You see? D60. So D60 is the diameter from which or through which 60% of the sample pass. Okay? Now what is D10? D10, the diameter, okay? D10, the diameter through which 10% of the sample passes through. Okay? So we have D60 over D10. By the way, D60 over D10, CU. Do you think, what is the minimum CU that we can get? What is the minimum CU? I will stop here. Why 1? Why 1?
Poor. More than
Poor? Good. Yeah. For example, the poorest way that we can have is a curve like this, right? The poorest way. By the way, can we have a curve like this? Of course not. Of course, no more. It's impossible. It's impossible that as a particle, after passing a sieve, it goes back to be not able to pass the smaller of the other sieves, right? So this is impossible. The theoretical possible way is to have like this. At this stage, D60, ED10 the same number, so D60 over D10 is 1. This is impossible, so we can say that CU greater than 1. Not greater than or equal, but greater, okay? Greater than 1. What is the minimum? This is, by the way, the minimum, sorry. Minimum CU is 1, greater than 1. And what is the greater CU? How much great it may be?
Infinity?
Not infinity, it's a big number. You are right. You are right. Suppose that we have a curve like this. So D60 is very big, D10 is very small, right? So we have big number. We cannot say infinity. Okay? Let us go back. So D60. No. Yes. So uniformity coefficient D60 over D10. Okay? Always D60 is greater than D10. Right? Right? D60 always greater than D10. The other one, we call it uniformity coefficient. Okay? Sometimes they call it coefficient of gradation. It's no problem. C sub Z, by the way, these are important. We will use them later, and you will see how we will use them. C sub Z, coefficient of curvature. It is equal to D30 square by D60. Okay, like this. Right. D30 square divided by D10 by D60. See? What is the minimum value? What is the minimum value here? Again, D60, D30, D10 greater than 1. Because D30, the same number, D60, D30, D10, right? D30, suppose X square divided by X, it's 1, okay? Right. So, D60, CU and C sub Z. By the way, D10 is called effective grain size. It is important to know. Effective grain size. We'll stop here and we will continue later. Okay? D10 is effective grain size. Remember this word, effective grain size. I don't have to tell you D10. If I said effective grain size, it's D10. Thank you. See you later.